The topic vectors in space is looking at vectors in 3 dimensions. So we have an x-axis, which is here, and I have a y-axis, which is here, and you'll see that we have now a z-axis. It looks like it's going up and down. So not only do we move right and left and then up and down, but now we might move in and out of the screen. So we have 3 different types of movement. So we're going to have an x and a y and a z now. So each point will have 3 values, and it'll come in what we call a 3-tuple. So it's an ordered triplet, if you will. So the x comes first, the y comes second, and the z value comes last. All right, so I have 2 points here. This one's hard to see. This one's 4, 3, comma, negative 3. But if I have these 2 points in 3 dimensions, and by the way, I will not ask you to graph anything in 3 dimensions because it's very difficult to do. But if we have these 2 points in 3 dimensions, and let's say that I call point A point 1, or the initial point of our vector, and I call point B here point 2, that's the terminal point of our vector. So let's say this is the initial point, and this is the terminal point. So I'm going to take this point and I'm going to draw a line connecting it to this point, and then put my arrow here. Okay, so that would be my 3-dimensional vector. If I have that 3-dimensional vector, how can I come up with the component form of this vector, or what we call the position vector? So you'll notice that this formula looks very familiar. When we did points in 2 dimensions, we had x2 minus x1 in front of I. We had y2 minus y1 in front of j. And so the new thing is going to be to do the same thing that we did with x and y. We're going to now do that with z. So we're going to do z2, or the z value from the terminal point. We're going to subtract off the z value from the initial point. So z2 minus z1, and we're also going to have a new letter for that 3rd dimension. We're going to call that k. So our component form in the ijk form looks like this. Okay, so let's do it with these 2 points. We want to come up with that position vector, or the component form of the vector. So we'll have our I, j, and k. Just going to do a little bit of labeling here. Okay, so I'm going to do x2 minus x1. Now x1 has its own negative, so it's going to be minus a minus. Okay, I'm going to do y2, that's 3, minus y1, that's 2. Okay, and then lastly z2, which is a negative 3, and I'm going to subtract off z1, which is 3. Okay, now I'm going to simplify, so that's 4 plus 2 in front of I, so that becomes a 6. I. 3 minus 2, that's a positive 1, so that's plus 1j, or just plus j. That gives me negative negative 3, that's a negative 6k, so that's minus 6k. So there's the component form of that vector. So now we actually have 3 different movements. How I like to typically think about this is a little bit different order than that. I like to think about my traditional x and y axis. So this number would tell you how much to go left and right. This number would tell you again how much to go up or down. But then I like to think about, and this is kind of hard to draw, but just imagine that you put your pencil right on top of that plus sign at the origin, and that the z-axis is actually coming out at you out the screen. So it's kind of hard to draw, but just imagine that was coming right at your face, and that's the z-axis. So this actually tells you how much to go in and out of the screen. That's how I like to think about it. So this would basically be going into your screen 6 units. So that's how I like to think about it. But once again, I'm not going to ask you to sketch these. Just going to ask you to work with them using those formulas. Okay, so we're going to start to see a lot of familiar formulas, like the formula for magnitude. Okay, if we knew the component form of a vector, now we have a, b, and now I have a third letter c to get that third component. The magnitude of that vector is going to be the square root of a squared plus b squared. Now once again, that should look really familiar. A squared, b squared, we've already done that. Now we're just adding in a third letter into that same formula, and now we're going to also do c squared. So let's find the magnitude of that vector v. It's going to be the square root of the first component squared, so 6 squared, plus the square root of the second component squared, so that's 1 squared. And now we're also going to square the last component, so the number in front of k, put that in parentheses, and then we're going to square that one as well. All right. Now remember also this vector could be written not only using that component form with the I, j, k, but also with the angle brackets. So we could also write this vector as 6, comma 1, comma negative 6. Remember, these two things are the same thing. They're both the component form of the vector, but one is using the ijk and one is using those angle brackets. And this should be an angle bracket. Okay, but they're both basically telling us the same piece of information, all three of those movements. All right, so in this case, here's our a, here's our b, and here's our c value. All right, so square root of, let's see, 36 plus 1, negative 6 squared is also positive 36. Let's see, that gave me 73. So our final answer here, v, the magnitude of vector v is the square root of 73. Right now, that's an exact value. If you want, you could put that into your calculator also to find an approximation. So the approximation, put into my calculator, I get about 8.5 if I round that to the nearest 1 decimal place. Right. So it depends upon what you're asked. Are you asked for approximation or exact? Make sure that you can give both. All right. Finding the dot product of a vector in space is actually pretty much exactly the same as it was when we were doing it in 2 dimensions. So we're going to take two vectors. We have vector v and vector u. And we have a1, b1, c1. Those are the numbers in front of I, j, and k for that first vector. For the second vector, we have a sub 2, b sub 2, c sub 2. And those are the numbers in front of I, j, k. Now, when we're asked to find the dot product, remember that we're going to see a dot in between the two vectors. We're going to take the first two numbers, so the number in front of I for each vector, and we're going to multiply them together. We're going to add that to the numbers in front of j multiplied together. So b sub 1 times b sub 2. And then now we're also going to do the same thing for that third number. The numbers that are in front of k are going to get multiplied together and added. So we're going to multiply c1 times c2, and then we're going to add that result in. This dot product again is a scalar, so just a number, not a vector. So that means when you get your answer for these, there are no I, j's, or k's in your answer. Okay, so you'll notice that the formula again is exactly the same as it was before, but now since we have that third number in front of k, we're going to do the same thing we did with the first two numbers. We're going to do the same thing with the third number. Okay, so really not a different formula, nothing new, just doing the same thing we did before, but adding on a third component. Alright, so our example here, given these two vectors, we're asked to find the dot product. So we have a dot in between the two vectors. So I'm going to multiply the first two numbers, so the number in front of I for each vector. So that's a 2 times a positive 1, right? So the number in front of I for vector u is a positive 1. So we're going to multiply those together as 2 times 1 plus. Now notice that I did not include the i's. It's just the number in front of the i's. Then we're going to do the same thing with the numbers in front of j. So we're going to take negative 2 and multiply that times a positive 3. No j's included. Plus, now we're going to take the numbers in front of k. So that's a positive 1 times a negative 4. We're not taking the k's. So we get 2 minus 6 minus 4. Our overall answer turns out to be a negative 8. So the dot product of those two vectors is a scalar. So what that means is that it's just a number. There's no direction associated with these. There's no I and j and k's. Okay, so be careful there. Don't include the I and j and k in that calculation. It turns out in the end just to be a single number. Okay, so more of the same. You'll notice that this formula is exactly like the formula that we saw in the dot product video for vectors in 2 dimensions. So it's exactly the same formula. So we can use this formula to also calculate the angle between 3-dimensional vectors. Okay, once again, we can't draw these. We're not going to draw them. I'm not going to ask you to draw them. But we can use the same formulas to analyze them, which is one of the reasons why this formula is so nice. Okay, so let's find the angle between these two vectors, vector v and vector u. To do that, remember that we're going to find the ratio by using this formula. We're going to find the dot product of the two vectors. All right, so let's go ahead and do that. It's going to be 5 times 1 plus negative 3 times a positive 7 plus a positive 4 times a negative 6. So that's what goes at the top of that formula. And then we're also asked to multiply the magnitudes of the two vectors underneath. So I'm just going to come up here. Let's find the magnitude of vector v. So that's going to be the square root of 5 squared plus the second component squared, so negative 3 squared plus 4 squared. Okay, so what is that? It's 25 plus 9 plus 16. Looks like I get the square root of 50. Okay, so we're going to multiply that in times what is the magnitude of vector u. So it's the first component squared, so 1 squared, plus the second component squared, so it's 7 squared, plus a negative 6 squared. So that's 1 plus 49 plus 36. So that gives me the square root of 86. Okay, we'll multiply that together. Okay, so we're going to do the same thing that we did before. I like to multiply those two square roots together underneath the same square root. If you have a different technique of simplifying from here, that's perfectly fine. But I'm going to go ahead and write that as the square root of 4,300. Alright, so I'm going to simplify across the top. That's 5 minus 21. And then, what is that? Minus 24. So I get negative 40 across the top. Okay, so I'm going to stop there with my simplifying because I do not know what the square root of 4,300 is off the top of my head. But I want to be careful of something. I know that this is the ratio. Okay, this is not the angle, this is the ratio. To actually find the ratio, I need to actually put that into the cosine inverse function, right? So I'm going to take this ratio and put it into the cosine inverse function. And I'm not going to round, I'm just going to use Desmos and let Desmos do all the work for me. Okay, so I'm not going to round that or try to approximate that. I'm just going to throw the whole thing into my calculator as is. Alright, so I'm going to go cosine inverse. I'm going to do negative 40. I'm going to highlight that. Divided by square root of 4,300. Okay, let's make sure we're in degree mode. There we go. So I get 127.6 degrees if I round to the nearest 1 decimal place. Alright, so we can see that a lot about this formula is exactly the same. We're just doing it with vectors in 3 dimensions. Okay, here's another familiar formula. We're asked to find the unit vector of a vector in a certain direction. So I am going to find a unit vector. Remember that a unit vector is a vector that has a length or a magnitude of 1. The formula is exactly the same as it was before. We're going to take the original vector and we're going to divide it by its own magnitude. And that's how we find our unit vector. So we're asked in this example to find a unit vector in the direction of this given vector v. So our unit vector u is equal to the original vector divided by the magnitude of that vector. So the original vector, 9i plus 3j minus k, and we're going to divide that by its own magnitude. So the magnitude of a vector in 3 dimensions, we're just going to take each component of that vector and we're going to square all 3. So I'm going to square the number in front of I, the number in front of j, and the number in front of k there, which is a minus 1. Okay, let's simplify that. That's 81 plus 9 plus a positive 1, because negative 1 squared is a positive 1, and I get the square root of 91. Now what we want to do is we want to have all 3 different numbers in front of those components. So I don't want to leave it as that vector divided by that. I would like to divide that square root of 91 into each component. So 9i divided by the square root of 91. So now this becomes the new x component, so the new number in front of I. Okay, so I want to make sure I do that division. Plus 3 divided by the square root of 91. Remember, that's like an implied 1 there, so that's like a minus 1 divided by the square root of 91. And we need our j there, and we need our k there. So we want to have a number in front of j, and we want to have that number in front of k. All right, now if you wanted to, you could rationalize. You could multiply top and the bottom by the square root of 91. That would be a preference. I would not require that you do that. Both of these answers are perfectly fine. Some people just like to rationalize. Don't forget your j and don't forget your k. So either one of those 2 answers is perfectly fine for the unit vector u that points in the same direction as the original vector v.